So the first part will give you a real overview what the eFMI technology is about. But I like to start with a short mentioning about the eFMI project. So it's a Modelica Association project. It's one of the open standards we have for the Modelica Association. And members are only organizations. We don't have individual members. And then you see there are quite a lot of organizations that are member in the Modelica Association project, eFMI. I think it's well represented from tool vendors to users. Interestingly, we have quite more users than tool vendors. I'd like to encourage always tool vendors to also support it because we have a lot of users that want something here. Yeah. So what is eFMI all about? If you think about it from the Modelica Association, also from the historic perspective, it all started with simulation. And simulation is your offline simulation on a very high level. So you write your equations down and then you can simulate a system. But even better, you do it in an object-oriented way. So you model with components and component libraries where hopefully if you have good library developers, users can do it by drag and drop. So they don't have to go to a level where they dig through the text layer. They can really conveniently use this to model their physics systems, multi-domain systems. And this is nice for offline simulation, and offline simulation can be quite heavy. And over all these years, sophisticated libraries have been developed. And these sophisticated libraries are also going to do virtual prototyping of a system that is to go to be developed. And every system you develop at the end is a cyber-physical system. So there's some piece of hardware involved here. There's a real plant, so to say. And of course, now you have this very advanced plant models. But as soon as you go to reality, there's also control. So you go into your physics-only models, and you add at some point some control into them somehow. And control is not necessarily physically; it's also a little bit imperative. Like if this or that state is reached, then do that. It has nothing to do with physics. So the sophisticated models got extended also with control, and then we're sitting here and looking. Okay, we have this cool stuff, and now it comes to the real development of the controller. What do? We write a requirements document in Word or something and hand it over to people that write embedded code. That's how I've seen it and heard it from a lot of companies. So they start from scratch developing a controller. But we have a very important asset here because we have all the models already. So why would you do this process? So the idea of eFMI is reuse the models you have to generate the code for control. And if we do that, then we can do very advanced control. Because we are talking here about models that are very sophisticated. We can do inverse model control. So for example, a typical industry use case is, yes, you have a value in your model, but not in reality, the sensor value is available. Let's say in an electric car, the battery, it has some heat, the battery cell. There's no heat temperature measurement sensor in the battery cell, but you would like to know how hot is your battery to control it better. Then you could do a virtual simulation of the battery faster than real time and reuse from this simulation the virtual sensor value. So you replace in your process model, take the physics from there, generate from them this predictor, get rid of the need for the physical sensor and inject that into your controller. So we have a lot of these things. We have virtual sensors, model-based diagnosis, like fault diagnosis. In the car, is my suspension still working? Is something broken? What is with the wheel? We can reuse our equation-based models to do inverse plant model design. So we reuse the physics and we ask the other question around, not how does the system simulate, how does it behave? We ask the question, what are the stimuli I have to give that the system behaves like this? And since Modelica is equation-based, you can do this kind of things. And then we get to things like model predictive control. So this is for advanced control. We are not trying to replace solutions that already exist. We would like to do something more advanced. Yeah? But of course, you can do also what simulate does. So the physical models, they are described by differential equations to describe the dynamics. And you can combine it with database modeling. And of course, you can use a reduced calibration effort due to physical parameters. So if you have an equation-based model, you can save a lot on the parameterization part. That makes it more easy. So if we compare this also with eFMI, eFMI is to exchange a simulation. So you have your simulation model and you generate a FMU, and then you can exchange it in the landscape with everybody that supports eFMI. So this is like we exchange a simulation. This is on the system level, can be very heavy simulations. It could be a model exchange where you have the need for external solvers to handle all these FMUs and so on. We are going much more, a little bit down to the question, how do we run a simulation model in hard real time in a safety critical system and generate code for that? And that's the important thing, generate code for it. So in FMI, whoever generates your FMU, he does it all for you, and then you get this like a black box. In eFMI, we are opening this because the question is, how do we get to a good workflow to actually implement a piece of embedded system? And that's the question here. So we are not necessarily on the domain of model-based systems engineering. I mean, it's part of it, but we are on model-based control. And then you're talking about things like AutoSAR, how you get it on the ECU, what do I have to do with my code to make it work in such restricted environment. And restricted environment, that's like the key term. So we have limited computation power, limited memory precision, fixed sampling rates that are very tight, static memory allocation, no dynamic memory allocation. We need worst time execution guarantees. It must be exception free. And we have to comply to a lot of standards like MISA, for example. If you do it a traditional way, then you need a lot of different engineers involved. So you start off, let's say, with your offline simulation model, where the physics are modeled, where you need domain knowledge about physical principles and dynamic models. Then you get to control engineering, where you also have a lot of system theory, stability, robustness. You talk about fixed sampling times, and if your controller is stable. Then you get to the numerics part, of course, because you get reduced floating point precisions. And at some point, you talk about on a very low level on my ECU, there's no operating system typically. It's a bare metal, and you have some software around it like AutoSAR, where you're supposed to embed your functionality in. Now, if you pull all of this on one person, he will die. That's why I know if you start today and you learn these things, in 10 years, you're finished with the last part, and then you can start with the first one again. So that needs a superhero, it's a problem. And instead, we say we have dedicated tools. So what do we have to do to bring this together? We standardize some interface where these tools interact. And that's what we then do. So we have a physics modeling expert, control engineer, and ECU software developer. And then we put eFMI that standardizes the interface where they exchange the artifacts for the development of what we call then the eFMU. So eFMU is not this one developer that presses a button and then there's the eFMU. It's typical. You hand it over to a lot of people. It's a white box. It's a development artifact, and they continue developing it. So this is also different to FMI, right? In FMI, you press a button and then you have your FMU. That's fine. We are not looking into this. The eFMU may not be complete. It may not be executable at the moment. There may be need that others come and help you and generate more things. Yeah, and the claim is that this will make people happy because every expert can be expert in his domain and contribute to the workflow, and you don't need this guy that oversees it all. So what happens is we try to automatize this process. So we start from a physical model, make, let's say, a reduced control model, then we generate some production code, and then at some point we deploy it on the ECU. But maybe before that, we do a software in the loop test of the production code. So you have an iterative process, right? You may get feedback like, okay, software in the loop test showed it's not really working. Then you go back to the control model design. You may see that the outcome is the code is too big. We can't deploy it on the ECU. Then we go also back to the control model design. So we iterate until all the requirements are satisfied. So eFMI is the open standard for model-driven development of advanced control function for safety critical and hard real-time targets. And of course, not every model that you have in Modelica is suited for that. So there will be the point when you see, oh, that model doesn't work out. That's not going to be deployed like this. You have to do changes on the model because Modelica is a general equation language, and there's even no theory when, let's say, a general equation system would, for simulation, terminate. It maybe get stuck in events and never get forward. You integrate until the error is small enough. That's a problem, and you can't do that on an embedded device because you don't have infinite time. Now you have an idea that eFMI is about bringing physics simulations to safety-critical real-time targets. And I'd like to talk a little bit about the eFMI standard. So how does it do it? It's a new standard enabling the application of physics models in embedded software. So it's this workspace where different parties contribute from a high-level algorithmic solution down to the embedded implementation on a dedicated target environment. Covers a lot of different concerns from implementation, testing, and integration. And in the eFMU, you have this in terms of different model representations. So one thing is, for example, we have a behavior model container that is about reference results. So you give reference trajectories, and this is what you expect the thing to do. That can be used then for software in the loop testing, for hardware in the loop testing on all kinds of levels. So typically in your simulation environment, with your offline simulation, you could define such reference results and add it to the eFMU. Then we have the algorithm code container. That essentially is a target-independent bounded algorithmic solution based on GALAC. GALAC is a new language in eFMI standard for safety-critical real-time fixed-rate sampling algorithms. The idea here is that your modeling environment, given your model, tries to transform it into a GALAC program. This may fail, this may not work, the model is too complex, but if it works, then you get all these guarantees. And you know, this is really suited for embedded. We didn't talk about the hardware yet. Maybe your hardware is not powerful enough to run it, but you know it has a burst time execution, and you know it has a fixed upper bound for the memory consumption. And then we have the production code container. That is when we transform the GALAC program to actual implementations, C implementations for the target. And then we have binary code containers where you could now compile production code to binaries for the actual target. This is how it looks like. You have the algorithm code, and then you can have arbitrary many behavior model containers, arbitrary production code containers, and binary code containers. And the workflow is roughly like this. You would start from your model. It doesn't have to be necessarily Modelica, but the tools we have at the moment are from the Modelica world, but other simulation environments are invited to support eFMI as well. It's not dedicated to the Modelica language. And there you could generate the behavior model from your offline simulation where you define, okay, this is the test scenario that must be satisfied. These are all my scenarios where I will test my controller. Then you generate the algorithm code. And then the simulation environment world stops. Then we come to generating from the algorithm code, actual C production code. There you have tools like Target Link or software production engineering from Dassault Systèmes, and Target Link is from DSpace. That can translate you this algorithmic solution to an actual C code. And then you could go to binary code for a dedicated platform, for example, AUTOSAR Builder, which would take the eFMU container and generate you for one of the production codes that you choose the additional code needed to make it an AUTOSAR component. And then it can also generate you the binary code for this AUTOSAR component, so you can deploy it in your AUTOSAR environment. And then we have all the other tools around for testing, which would, let's say, take the behavior model like TPT to conduct the test, processor in the loop, hardware in the loop, software in the loop test. And we have the system integration, where you bring the thing on the concrete embedded target. And this all of this development is iterative. So you may iterate, and the cool thing is, since most of these steps are automatized, you can do very fast iterations to meet your requirements. You have many deployment scenarios for the eFMU. The most simple one is, if you have an eFMU with working production code, then you just say, okay, I want to have it as an FMU. And that's simple. Also in Daimler, it's just one function you call it, it wraps you up as an FMU. And then you can exchange it with other FMU environments. However, there are other scenarios, like tool-specific ones. For example, we support also that you import a production code container in Simulink. That's also possible. So in Daimler, you can, again, call a function that generates you a script that you can use in Simulink to import this very production code. And then it's a Simulink component. It's a Simulink C function block. So it just uses the production code as is. It's not touching it anymore, but you can, of course, a Simulink model around your other blocks and use your embedded code generation facilities, and it will properly integrate everything, and you can use it as for deployment. And then we have, of course, other things like customer-specific software integration or target-specific binaries for some type of ecosystem. And you see that FMU is also interesting because you have all these things that support FMUs like cloud or clusters or simulation. The important thing is that eFMI is about one embedded functionality. This may be a very complex embedded functionality like a virtual sensor that simulates, let's say, your battery management system. So it can be a lot of code, but it is still just one functionality. And if you look into the embedded world, there's of course always the question, how do you system integrate all kinds of functionality? So you have a distributed system with hardware, then you have needed a scheduling and a timing and all these things, and you have a CAN bus communication and all this stuff. This is not what eFMI is about. So there we say, reuse your existing standards. So you can integrate it in AUTOSAR, you can integrate it in the ASAM standards. That's up to you because there are so many different system integration scenarios. But we started to support some of them that you get one-click solutions, but it's basically an infinite number of stuff we would have to do to support them all. It's really a huge field. Now you know the EFM standard defines model representations capturing embedded software development stages, leaving finding solutions to the expert tools. The question is, but how does the eFMI standard enable an automated tool chain, satisfying all these functional, safety critical, real-time objectives? And now we are looking a little bit into what you really have in these containers. I can't dig in too much detail, but it should give you a rough overview of what is there. The first thing and most important is this algorithm code. That's like the starting point for any further code generation, where your simulation tool has to generate algorithm code. And this is represented in this Gallic language, which is an imperative, target-independent language with a high math abstraction level, like you have multi-dimensional arithmetics. You can just say, I want to multiply this matrix or with this vector. And you have a lot of built-in functions like solve a linear equation system. It's well-designed and decidable semantics and safe numerics. It has a guaranteed error handling. So we will check that all the errors that could happen are somehow captured, so including non-errors. And it is a rather simple language, meaning in terms of if you from a simulation environment want to generate Gallic code, this is nice. It's a nice intermediate representation to represent your like algorithmic solution of a simulation in Gallic. But it's also a good starting point if you go for further C code generation or downwards towards the embedded device. Gallic as an intermediate representation also enables you to do a lot of optimizations. So for example, we know for every 2 Gallic statements if they can be swapped. You know what that essentially means? That means you can do massive parallelization. Because you can swap the stuff around, you make round blocks, and then you decide in your production code generation, this runs on this core, this on this core, this on this core, and you just parallelize it. That's possible in Gallic because we can give you this guarantee. We can't give this guarantee for general C code because you have the alias problem and the pointers and stuff and this and there. But in Gallic, we can decide this kind of things. So it's a nice intermediate representation for code generation. And this is how it looks like. You have the Gallic program, and then in the algorithm code container, it looks like a little bit like Modelica, but it's really only algorithms, imperative. And there are also improvements compared to Modelica, like the error handling on this one. So it's not a Modelica subset. So you have your inputs, outputs, tunable parameters, and then you have the inner states that have to be kept from one sampling step to the next. So these are states in terms of programming. So if you do samplings, sometimes you need to know, oh, this was my state at the last sampling. So you have to keep the value. These are not necessarily physical states. And then you have the interface methods where you can interact with it, like to do a sampling step, to compute for the inputs, to new outputs, to do a recalibration. If you have new tunable parameters to recalibrate all the dependent parameters, you can do reinitialize if something goes wrong in your embedded system. At one time, you know always, okay, if this thing comes from Gallic, then I have this reinitialize function where I can just restart the thing and this is safe. And then we have a manifest where you have all kind of meta information, like the checksums for the generated code file, documentation derived from your model, potentially. You have IDs for referencing different stuff. You have the units described for in and outputs. This is very much like the model description in eFMI. The interesting thing is that this Gallic has a common interface with a well-defined life cycle. So that means we have a way to default initialize the thing. We have a way to do the sampling, how we do recalibration, how we do reinitialization. There is a state chart in the eFMI specification standard that kind of defines you all the valid system integration scenarios, how you can interact with this Gallic code. This is important because only the Gallic code has a standardized interface, not the C production code. In eFMI, the C code has a standardized interface, not in eFMI. And the reason for that is because if you go to different embedded systems, they have different requirements on the C code. And you can't just standardize the C interface. It's not possible. It may start with simple things like naming schemes, where you have to satisfy certain naming schemes. But it may be also things like, are you permitted to have global variables in your C code? Must it be structured in structs? Do all the runtime values have to be in one big array collected, or can you distribute them, and so on and so on? So we can't standardize the C interface. It's not possible for the embedded world. But we have a standardized Gallic interface. And what you see is, okay, for this input, for example, in the manifest, you see this input, it has this unit. And then you know, okay, that's the unit. And you also see the causality that it is an input from the manifest. So the interface is described in the XML manifest. You can see it in the Gallic code, but you can also just look in the manifest. So you don't need a full Gallic like compiler that reads all kinds of Gallic programs to know what the interface is. You can just look into the manifest. And the Gallic code is like the starting point of further code generation. Yeah, so it has to be generated by the simulation tool, modeling tool. And we have all these implicit language guarantees that when you have a Gallic code, okay, now you can come with your production code tool and do whatever code transformations you want. It may not be possible that a static code analyzer shows you that this code is safe, but we know that it comes from Gallic, so we know it has these guarantees as long as your tool is not broken, right? But this is the thing you always do not assume. You don't assume that your compiler's program generates your broken binary. So you can assume your tool is correct, but coming from Gallic, we get all kinds of guarantees for this program. The next thing we have in the eFMU is the behavior model. Yeah, it's a similar idea. We again have the XML manifest that describes you what are my test scenarios, what are the different trajectories for my test scenarios. It describes you how the trajectories are represented in a comma-separated value file. So how do my in and outputs on which column in this comma-separated value file do they map? Also, if you have multi-dimensions, how they are spliced off across several columns. And you have documentation. You define the tolerances in the manifest. What are the tolerances for my outputs, for example, such that it still passes. And you can also define the time grid. The behavioral model features documentation and test scenarios in the manifest. It has, again, well-defined units and types. It has a well-defined mapping of each variable's dimensions to individual reference trajectories. We have 3 types of tolerances we support: absolute, relative, and you can even define your own trajectories with an upper and lower trajectory within which the value must be. And we have 2 types of trajectories with respect to time. We support equidistant time. That is really hard fixed sampling time. So within this fixed sampling time, you have in the reference trajectories values, let's say every millisecond. But we also support variable. That is what you usually use if you come from the simulation world. Where then if you would want to know the value of something in between, where you have 2 reference points, you do interpolation. And interpolation is fixed in the eFMI standard how you have exactly to interpolate. So the tools are not free. The same test scenario is run with different tools. They will agree what the value will be. And then you have the comma-separated value files to represent the actual trajectories. The main point is the behavior model has a unique interpretation. It's really nailed that you will never run into a scenario that one test tool says the test passed and the other said it failed. And if you think about it, that's really tricky to achieve because we are talking about things like floating point imprecisions. When you say you have an upper, a min, and max within which this value can be, if the tool computes this somehow as it pleases. You may have this very slight floating point imprecision in the one tool. It just happens to be that the result on that point, and the one says yes, pass, and the other says no, it doesn't pass. That's not going to happen if the tools comply to the eFMI standard. The tricky part now is we have the algorithm code and we have test scenarios for it. And these two are linked because the one manifest for behavior model links back to the algorithm code. And essentially, if we look into this manifest, then we see, okay, we have a description of our scenarios. And this scenario has a mapping, how it is mapped to the CSV file. So how the trajectories are represented. And then we can see, okay, thanks to this, we know that for this variable, it's this column here in our CSV file where we have the trajectory. And then we can also look up which unit this is supposed to have. And this is important, right? Because this unit here doesn't have to be the unit we have here in the algorithm code. And then you see, okay, this maps back via foreign reference to the algorithm code manifest, to this one, and it's actually this variable in it. So this trajectory here is the trajectory for this variable in our Gallic code. And this here in the algorithm code, it has this unit. And this unit may not agree, but they must according to the eFMI standard. And why is it important that we model it for both? Because we have to check consistency. Because if you look at the eFMU, somebody may generate algorithm code. And somebody comes and generates a behavior model for it. Then you regenerate algorithm code. Now it uses different units. If you wouldn't take care of this, and then you have the behavior model which assumes the old unit, then you would get very funny test scenarios where things may pass or fail and you don't know what's going on. So they both have their own units, and now we can check the consistency. Are the units really consistent? Does it really match? Or do I have to regenerate a behavior model or regenerate an algorithm code? And you do even know which one you have to regenerate because thanks to the foreign reference, you know which of the artifacts is stale. So this is important. The same holds for sampling periods. You may change the sampling of your controller. Then you get your algorithm code, and the behavior model maybe has an equidistant time grid, but the equidistant time grid must perfectly match the sampling time of the controller. Then you get again, you do not comply with the eFMI standard, and you get a message, okay, this is not correct. And then we come to the next container, the production code. Idea is the same. We have the C code, that is arbitrary C code, whatever your production code will generate it. But we have the manifest, where we know this, where the manifest now describes the interface of that C code, and it links it back to the Gallic code. So the production code documents the C sources, their dependencies, global entities, and interfaces. The C data layout and interface are not standardized. So you can have various different target environments, but it links the C code to variables and functions of the algorithm code manifest. And this links implement kind of this Gallic block life cycle, and that describes you how to system integrate this very C code. So let's think about it. We have our Gallic code and a manifest, and we have the C code. And then, for example, we have this global variable reference, and we see, oh, this is going to a struct, components inside the struct, and they map back by a foreign reference to this Gallic code, and that's the variable u. So, okay, my variable u was put inside the struct. And then you know, okay, following all these links back, how to system integrate your C code. And we kind of do this automatically, for example, if we export from Dymula towards Simulink. Yeah, then we look for the manifestors, and then we know which kind of code to generate on the Simulink side to embed as a C function block this production code. Yeah, and then we have a binary code container, same idea. There you have just binaries, they're like a black box, but a manifest. And this manifest documents the binaries, how they have been built, they use compiler, linker options, and it links to the production code container. And now comes the interesting point. When we look back at testing and system integration, how does it go? So we have some behavior model and we have some production code. We want to test them. They both link to the algorithm code. And now we can see the connection, how to system integrate, how to instantiate this production code or binary code to test with this behavior model container. And then we can conduct this. So we match behavior model with production code containers via the indirect linking, and then use production code Gallic interface linking for the system integration and testing. So in summary, if you think about the eFMI standard, it's, in my opinion, the standard for open standard for model-driven development of advanced control functions for safety critical and real-time targets. It has a container architecture with the well-defined model representations on the different abstraction levels. It has the abstraction level from the expected behavior to the binary code, from the implementation to system integration. It enables you collaboration between the different stakeholders that have their own different toolings. They exchange the eFMU. They are working together. And then we have all this kind of traceability between the different containers and the checksum, which enable you to see if an artifact is stale, has to be regenerated. And this means you can automatize the tool chain. And we have the algorithm code container that gives you some guarantees about the safety. And once an algorithmic solution is found by a modeling tool generating algorithm code, this is not a trivial task, very complicated. It's an open research question for many things. But once you have a Gallic representation, then eFMI conveys this down to the embedded solution. In a sense, it is a simple standard because we only talk about what has to provide it, but we don't say how the tools achieved it. So the magic is really in the tools, and it's also simple because there are no optional features. The tool complies or doesn't comply. It's not like, this could be supported, but another tool doesn't support it. No, it has to comply. So the magic is in the tools, and they can be expert in their respective domains. This was a very rough going through the eFMI and the general idea. So now you know, like what I say, what the standard is, what are the paragraphs. Now we want to start with some practice. For that, we have a running use case.